Welcome to the Organic Chemistry Podcast, Dr. Brian Lloyd's scribblecast of organic chemistry lectures and solutions to homework problems. In this scribblecast lecture, we'll be examining enolates and carbanions. You may be wondering why we're covering enolates and carbanions in the carboxylic acid section of the course. It'll become quite apparent. There are several very important reaction mechanisms involving enolates and carbanions for carboxylic acids and carboxylic acid derivatives. But to begin with, we'd like to review all of the areas of carbanion chemistry that we've covered, or enolate chemistry that we've covered so far in the course, and try and pull it all together. Carbanions are reactive intermediates in which the carbon possesses a pair of non-bonding electrons, such as, for example, you might have CH3 with a lone pair on it and a negative charge, hence the term carbanion. They're extremely strong bases, very powerful nucleophiles. Now, carbanions can be generated in two main ways. The first way is to generate it via organometallic chemistry, or from organometallics. Now, we've covered several different types of organometallics. We can take alkyl halides such as Rx and react it either with two lithiums in ether and make R-lithium, an Alkyllithium reagent, plus LiX. Of course, X can be chloride, bromide, or iodide. Or you can react it with magnesium metal in ether and prepare a Grignard reagent, such as R-magnesium X. Both reagents, Alkylithiums and Grignard reagents, are good sources of alkyl-. Now, they represent powerful alkylating agents. If you use either of these reagents, either the Alkylithium or the Grignard, you can produce, if you react with carbonyl compounds, react them with carbonyl compounds, you can produce alcohols, or if you react them with the CO2, for example, you can produce carboxylic acids. Carboxylic acids. Now, we can make milder alkylating reagents. For example, we can take two Grignard reagents, RMGX. If we take two Grignard reagents plus cadmium dichloride, we can make Alkylcadmium, Dialkylcadmium reagent, and we'll get to magnesium X. Okay, chloride. Now note, R must be equal to methyl, primary, or phenyl. Okay. Now, I'm running on reserve power, so I have to plug in my laptop. Here we go. Okay. Now, note dialkylcadmium when reacted with an acid halide, such as an acid chloride, is a milder reducing agent and won't go right through to the alcohol. It will stop at a ketone. So it's a nice way to make a ketone from an acid chloride. You can do a similar reaction with a dialkyl copper reagent. But the dialkyl copper reagent is prepared from 2 alkyl lithiums. Dialkyl copper is more powerful than a cadmium reagent as an alkylator, but it's weaker than a Grignard. It's reacted with cuprous iodide, the 2 alkyl lithiums, and you produce a dialkylcuprate, a lithium dialkylcuprate. Now, lithium dialkylcuprates fall somewhere in between Grignard reagents and dialkylcadmium reagents with regards to alkylating power. And lithium dialkylcuprate will react either with alkyl halides to make an alkane, or an acid chloride Note, the reaction with acid chloride occurs at 0 degrees C to minus 78 degrees C. And you will get a ketone. The dialkylcuprate is usually used only when, if and when the dialkylcadmium reagent can't be used because it's restricted to methyl primary phenyl reagents. So organometallics can be used as a source of C- if you like, and we've looked at a wide range of reactions and functionality utilizing these organometallics. But another source of carbanion chemistry is the formation of carbanions because of the loss of alpha-hydrogens from carbonyl-containing molecules. Enolates, if you like. Now, one that would be related to carboxylic acid derivatives would be the utilization of a diester, such as diethylpropanedioate or diethylmalonate. For example, if we draw that molecule, diethylmalonate, we have two ester groups, ethyl esters, and we have a CH2. Now, next door to the carbonyl is this alpha carbon. And if I hit this molecule with a powerful base such as ethoxide, always remember, if you use a alkoxide base, you must use the conjugate acid as that base's solvent if you want to make sure you have ethoxide in solution. So HOCH2CH3. Ethoxide will deprotonate the carbon, producing a CH minus. We now have a C double bond O, OCH2, CH3. Now you might be wondering, why would this happen? Does not alkyl oxide react with ester to do transesterification? Would we not get a transesterification reaction rather than this deprotonation? Well, in fact, we probably could, and that's why we chose ethoxide. We chose ethoxide because, as our base, because we have an ethyl ester. If ethoxide attacks the carbonyl and forms a new ethyl ester, it kicks out ethoxide. So in other words, transesterification gets you nowhere. The base attacks and you get the same base back. So eventually, outside of the transesterification reaction, you're going to have a base which can attack this alpha carbon and deprotonate it. Now, normally, alkane-like carbons are not very acidic, and they would not tend to lose a proton. And yes, this is a carbanion, but the only reason this carbanion forms is because it's resonance stabilized by the carbonyl. I can draw a resonance contributor for this molecule. And that resonance contributor involves dumping the lone pair to create a double bond between the CH and the carbon, and then we move these pi electrons out onto the oxygen and create an O-, an alkoxide. An enol that's deprotonated is called an enolate. And so we are resonance stabilized with the enolate. So we have an enolate. The other resonance structure, of course, is a lone pair dumping the other way, the other pi electrons moving out. We get an O- on the other side, a double bond to the CH, and then a C double bond O. OCH2, CH3. So what you see here is a resonance stabilized carbanion. Now, this type of deprotonation will work well with esters, but not carboxylic acids. If we had the dicarboxylic acid malonic acid, and we react it with a powerful base such as ethoxide, instead of deprotonating the alpha carbon to the carbonyl, the far more acidic protons are on the oxygen. You will produce the dicarboxylate, and you will not get deprotonation of the alpha carbon. So this cannot occur when you have carboxylic acid, but it does work rather nicely with the ester. You should also note that the nature of the R group here is not crucial. I could rub out the OCH2CH3 and replace it with R substituents. So let's do that. And that opens up this chemistry to far more than just the diester. R was, okay, R did equal OCH2CH3. In fact, it could be an O-alkyl group. It could be any carbon chain here. So you can have a diester. R could also equal alkyls, such as CH3. Or R could equal a hydrogen. And the R's, in fact, could be different, where you have one as an alkyl and one as an ester. In other words, notice that one carbonyl is located from the alpha beta from the other carbonyls. So these are beta dicarbonyl systems. So we could have beta diesters do this, an ester group of both functional groups. We could have a beta ketoester, okay, a beta ketoaldehyde. They could be different. We could have a ketone and an aldehyde. A beta aldehyde ester. A beta dialdehyde. Or we could have a beta diketone. In other words, as long as there's no proton on this oxygen that is located here, as long as you don't have an OH group, you could have a carbon or an ester group on either side, you can generate these types of carbanions. Now, carbanions formed by these molecules can act as powerful nucleophiles. However, because of steric hindrance, they cannot react with secondary or tertiary alkyl halides under SN2. Nevertheless, in spite of this, the acid strengthening effect of carbonyl groups to these alpha carbon hydrogens is a very important feature in organic chemistry. Let's take a look at the type of reaction that one could actually do that would allow you to do some interesting organic synthesis because of this carbanion chemistry. Well, obviously, if we start with the diester, and let's use the ethyl, I'm going to use R in this case equals CH3 CH2, okay? So R will equal that. So I'm going to have an RO C double bond O CH2 C double bond O OR. And I'm going to react this with sodium ethoxide. So I'm going to have OCH2CH3 minus as my reagent. And of course I've got to use that in methanol. Very important to use the same base as the ester group and make sure the alcohol solvent is the conjugate acid of that base. Well, of course, as we've shown, this guy will form a carbanion. That is resonance stabilized. Now we've already drawn the resonance structures, so I'm not going to draw those again. Okay. Now this carbanion in step 2, so step 1 is carbanion formation. In step 2, so this is step 1, and it's called carbanion formation. In step 2, we can react this carbanion with a primary alkyl halide, such as propyl iodide. If we do that, we get SN2 attack. So step 2 is SN2 on our primary alkyl halide. And what we now end up with is RO, C double bond O, CH. C double bond O, OR. And off of the CH is a CH2, CH2, CH3. We have a propyl group attached. Now we can repeat this process again. We can use the same base, OR minus and HOR. And if we do that, we'll get RO, C double bond O, C lone pair minus C double bond O, OR. Pull the second H off. Now notice you can't do this step all at once. You can't pull both H's off at the same time. That would be too much negative charge on that carbon. So you do it stepwise. You pull one H off and then you pull the next. Okay. And we could repeat that now with a different alkyl iodide. We could repeat step 2. So basically we're repeating step 3 and step 4. Step 3. Step 4 just repeats of steps 1 and steps 2. So we now hit step 2. And this time, let's say we use a butyl iodide. Another primary that will go SN2 really well so we don't have steric hindrance problems. And we'll go SN2 and we'll get substitution. And when we're done, we will have RO, C double bond O, C, C double bond O, OR. And off of this middle carbon now we have a propyl, and a butyl. Great. Now for step 5, okay, step 4. Step 5 is simply hydrolysis of the carboxylic acid in acid, or of the ester to make carboxylic acid, of the carboxylic acid derivative. Hydrolysis of the ester groups will make a dicarboxylic acid. And we'll get HO, C double bond O, C, C double bond O, OH. And I'm going to write this as C3H7 and C4H9. My butyls. Now we've already learned that if we apply heat to a dicarboxylic malonic acid, we can undergo beta-decarboxylation. Remember, we kick out a CO2 and we put the H here. And so what that will produce is a C double bond O, OH, we'll have C4H9, a C with a CH2, 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 CH3, so there's our butyl group. And we'll have the propyl still on. And we'll have an H that came on here. And we'll undergo beta-decarboxylation. In fact, you can do this beta-decarboxylation in one step by hitting it with acid at the same time you apply heat. So what we see here is a carbanion from a malonate diester doing nucleophilic addition to make substitution, and then we do a combination of hydrolysis of a carboxylic acid derivative with beta-decarboxylation. This is a beta-decarboxylation. And we'll look at those mechanisms again. And if you do this reaction, enolate carbanions let you make a brand new, fully substituted, large, organic carboxylic acid from a diester. So you can do quite extensive chemistry because of the formation of such a carbanion. Now, I'm not going to look at the hydrolysis step again. We've just covered that. You can look at the hydrolysis reactions. We looked at it in acid chloride chemistry, and hydrides, esters, amides. This is the hydrolysis of an ester. We've covered this mechanism for step 5. It's in your notes. You can look at it. I do believe, however, it's worthwhile looking at the beta-decarboxylation step one more time for a molecule that has 2R substituents here. And so, while we leave this last step up, I'm going to, at the top here, make some room, and just show the mechanism once again for that beta-decarboxylation step. Okay. So essentially what happens is I'm going to redraw this carboxylic acid, show some lone pairs here. And what you can see is that the OH is in close proximity so as to hydrogen bond to a lone pair on the oxygen, so that when heat is applied, when you apply heat, you can get a pericyclic movement of electrons. That is, electrons can go here. We can break that CC bond, and these electrons can move in such a manner. Now this means I can draw a transition state. I'll use different colors for bond forming and bond breaking. We have an H, a C, and this bond's not there. C, O, and we have an OH. We also have our C4H9 and our C3H7. Okay, so now what we're going to do is use some different colors. I'm going to use black for bond forming, And so we are forming a pi bond here. We're forming a bond to the hydrogen, and we're forming a pi bond to this oxygen. I'm going to use red now to show the bonds that are breaking. We have a pi bond here that is breaking. We have a carbon-carbon bond that's breaking. And clearly we have a bond to hydrogen that is breaking. So, in my transition state, this is a transition state, so I draw in my square box, put my double dagger. Black was bond forming. And red was bond breaking. And this mechanism we covered in carboxylic acids is known as beta-decarboxylation. It's a paracyclic movement of electrons. If I show the electron movement in black, so it stands out a little bit from here. This pi electron shifting this way. This carbon-carbon bond breaks. It makes a pi bond to the oxygen. The oxygen OH bond shifts to the other oxygen. You get a circular movement of electrons. When you're done, what you end up with, if I draw everything in the same orientation, is a carbon dioxide molecule given off. So there is plus CO2 gas here. And you get a carbon double bonded to a C, which has two OHs. You produce an ene diol. And so you have C4H9 and C3H7. Oops. And you make this carbon dioxide and this ene diol. So you get an ene diol. Now the ene diol is not stable and tautomerizes to a carboxylic acid. The H ends up shifting over here and you get a double bond O. And you get this carboxylic acid. Beta-decarboxylation is very important and can be used to synthesize carboxylic acids from dicarboxylic acids. Now, let's look at this mechanism again, but with a little modification. A little modification. Because I can do the same things on ketoesters. You'll notice that I didn't have to have a diester. I could have had a molecule started like this, where I have a ketoester. R again will be ethyl. Okay. And if I hit this with sodium ethoxide, OCH2, CH3 minus, I can make the carbanion. Again, it will be resonance stabilized to the carbonyls. It doesn't matter whether the C double bond O is part of a ketone or an ester N. I can draw two enolates for this. Just like in the previous reaction, I could do an SN2 with propyl iodide, propyl bromide, some kind of X group here. Let's use bromide this time. Do an SN2, and when I'm done, I will have CH with a propyl group off of it. So the exact same reaction works with various functional groups. It does not have to be a diester. This substitution, I can get this far. The last step, acid hydrolysis. Well, of course, acid hydrolyzes ester to carboxylic acid. It does nothing to the ketone end. We get carboxylic acid. Now this is where you note that if we heat this, we can turn this OH around so it interacts. We could draw a transition state or an intermediate state where the OH, let's put C3H7 here, interacts so as to give me that same type of transition state. I can get to this, and this hydrogen bonding to this oxygen. So long as there is at least one carboxylic acid, this guy will go on, will kick out CO2, and in this case we would make CCH3, C double bond O. The H would add to this CH, so we'd have a CH2 and a C3H7 plus CO2 gas. So if you use a beta-KetoEster, instead of getting a substituted carboxylic acid when you beta-decarboxylate, you get a new ketone. Okay? You get a new ketone. Now, just a warning about this, you got to have at least one ester group. If you had a diketone here, if this was a CH3, you would stop at this diketone that was substituted because there'd be no OH could do this type of beta-decarboxylation. Okay. Well, this type of carbanion chemistry has really been a main area of focus in the lectures and scribblecasts so far or today, and we're going to review some of the previous reactions that we have observed this type of chemistry in. And the first set of reactions we're going to look at that actually involve this type of chemistry was the alpha-Halogenation reactions that we looked at for aldehydes and ketones. Alpha-Halogenation of aldehydes and ketones. And remember, we had both scenarios, one in acid, one in base. And we learned in acid would increase the concentration if we had a ketone like this. Acid would increase the concentration because of protonation, increase the concentration of the enol. That is, we could protonate the carbonyl And we could deprotonate the carbon if we did, we'd get this. And I can dump that lone pair because it's the charge separates resonance stabilized and form the enol. So because of acid protonation of the carbonyl, you actually get a slightly higher concentration of enol than normal. Now, we can alpha-halogenate from the enol. And the reason for this is the resonance stabilization of the carbonyl, if you like. Can attack the X. X gets polarized, and you will produce the protonated alpha-halogenated species. X plus X minus, and X of course can be chlorobromoiodo. And then of course the last step is deprotonation, minus H plus. Now, we learned that the first step in enol formation is deprotonation. Or the first step is protonation and of the oxygen on the carbonyl. And if you have an electronegative atom, that's going to interfere with that process because the carbon will get a delta plus, the electronegative oxygen's orbitals will shrink, they will become less basic, and this protonation step will be slowed down. So subsequent halogenations are difficult in acid. If we tried the same reaction in base, reaction proceeds somewhat differently. Alpha-halogenation in base requires enolate formation and involves deprotonation of the alpha carbon by hydroxide. Now clearly this doesn't happen to a great extent, but there is the possibility of forming a small concentration of CH2 minus. And the reason for that is the carbon minus, or carbanion, is resonance stabilized with the enolate anion. Granted, concentrations are small, but the presence of hydroxide will increase the concentrations of the enolate. Now, what happens next, of course, is attack on the halogen. And you can actually have the pi bond reform and this pi attack, or you could look at it as the minus attacking. Either way, you get back to RC double bond O CH2X. Now, unlike acid, the fact that the base must deprotonate to make the enolate, and that this reaction rate is controlled by the concentration of enolate, the fact that you put a halogen here that will stabilize because of electronegativity, the formation of the negative charge, the next attack with hydroxide goes a little faster. In other words, the formation of this enolate is a little more stabilized than the previous one because of the electronegative X stabilizing the anion or deprotonation of the CH. That result is subsequent alpha-halogenations are favored. And we discussed this in aldehyde and ketones. And this led, if we repeated this process, this would eventually lead and if we repeated it again, we eventually get if we have a methyl ketone, tri-substitution. R C double bond O CX3. Well, X could be, for example, iodide. Now you got to remember this whole reaction happened in base, so we have hydroxide around, and hydroxide's not just a base, but it's a nucleophile. I could form this. Okay, so we have RCO minus OHCI3. When the carbonyl reforms, it can kick out CI3. Now you might argue and say, wait a second, carbon is a terrible leaving group. In aldehydes and ketones, we don't do nucleophilic acyl substitution, we do nucleophilic acyl addition because H and carbon, being negative, won't leave. Except in this case, with CI3, you have 3 electronegative iodines that help stabilize the carbanion that you kick out. And so you get RC double bond OOH in this last step. Plus, you get CHI3, which is a yellow solid. Whoops, sorry, CI3 minus. Now this goes on, CI3 minus will deprotonate the carboxylic acid, giving you carboxylate and CHI3. CHI3 is iodoform, it's a yellow solid. This is the iodoform haloform test for the methyl ketone. The formation of a yellow precipitate indicates the formation of a yellow ketone. Well, I think this is a good place to stop with regards to this type of Carbanion chemistry. We'll continue with our examination of enolate-based carbanion chemistry. Next lecture we'll review the aldehyde-ketone reaction called the Halogenation reaction. I'm Dr. Brian Lloyd. This is my Scribblecast. I thank you for listening.